So good morning all. Today we will be looking into the lab assignment 1, which is a study assignment, a study of a deep learning packages like TensorFlow, Keras, Theano, and PyTorch, and then document these distinct features and functionalities of the packages. So looking back to this particular, so today this part we will be teaching through the a PDF. So I have noted down the characteristics, then the architecture diagram, the features of all these packages which we require to study for our deep learning lab or the LP4 lab. So let us see. We will go back to little basics of these packages and then come back to the individual packages also. Let's start with the basics. So we should know like why a deep learning framework is actually there. So before comparing these four packages, let us understand why they all exist. So when we build a neural network, we are ultimately doing a huge amount of a matrix arithmetic. So multiplying the numbers together, adding them, passing them through the nonlinear functions, and then during the training, computing how much each individual number contributed to the final error. So this is what happens generally in the neural network. Correct. So then when we find this final error, what we do that error is like we can adjust it slightly. So doing this arithmetic by hand for a network with a millions of a parameters is not a humanly task, right? And so we require the frameworks like the TensorFlow, Keras, Theano, and the PyTorch, which exist and they handle these things automatically. So representing the data as a tensor and then computing the necessary derivatives automatically through a process. And this process is called as the automatic differentiation and making efficient use of the specialized hardware such as the GPUs. So this is what is all is my automatic differentiation. So everything else in this document which we will be looking into is going to move around into this philosophy only. Now before going in a deep, let us understand what is this tensor. So let me take you to the topic which is called as a tensor and why we always called it as a tensor. Okay. So here we have the little reference about the tensors and let me explain you what is this tensor. So the tensor, it is the most fundamental term in this particular field. It is a simple a container for a numbers. So generalized to any number of a dimensions. For example, a single number like a value 5, which is called as a scalar or which is also called as the zero dimensional tensor. Right? Again, I will repeat a single number like a value 5. This particular value is called as a scalar and it is also called, it is also called as the zero dimensional tensor. A list of a numbers like 1, 2, 3. It is a vector or a non-dimensional tensor. A grid of a numbers like a spreadsheet and is a matrix or a two-dimensional tensor. A stack of a matrices. So we have this stack, a huge stack, one matrix above another. It's like a batch of the matrices, a batch of the color images, we can say, as for example, right? Each with the height, width, and the three color channels. So it is a three or the four-dimensional tensor. So this is all. This is the data what we pass. It's called as the tensor. So every single piece of a data that floats through any of these frameworks, whether it is an input image, a set of weights, or the computed gradient, it's represented as a tensor. I hope this term tensor is clear with all of you. So tensor is simply it is a data which is passing through the network. We can have the single number which is called as a scalar. We can have the two numbers which is called as a vector or a one-dimensional tensor. Even there are the grids, there are the matrices, a stack of the matrix, color images. So all this data is a tensor. It is a one-dimensional, two-dimensional, three-dimensional, four-dimensional. So every single piece of a data that flows through any of the network, any of these frameworks, neural network frameworks, whether it is an input image, a set of weights, or the computed gradient, and all these terms are called as the tensor. So with the diagram also you can see this. First, the TensorFlow was created by the Google Brain and it is released in 2015. Its name comes directly from its core idea that tensor flows through the system along a graph of the mathematical operation. So the document mentioned that TensorFlow was a computational graph based and originally used a static graph. It is also called a define and then run model, right? So here you can see that what that means in the plain language. So in the earliest version of the TensorFlow, that is my version 1.x, we would first write the code and then only describe the computation we wanted to perform. For instance, take this input and then multiply it by this weight of matrix and this is bias, then apply the activation function. So this is one by one we describe the computation to the code. So without actually numbers being computed. So this description got compiled into the fixed structure called the graph. Right. I hope you are getting this. Again, I will explain you. Look at the graph and then I will explain you what used to happen during the version 1.x of the TensorFlow. So during the version 1.x of the TensorFlow, there we first write the code that only describes the computation we wanted to perform. For example, take this input, multiply it with the weight matrix. Then this bias is to be added, then apply the activation function. So without any actual numbers uh, being computed, this particular structure is getting compiled. And this structure which is getting compiled is called as a graph. So only after the entire graph was fully built, only after this entire graph is fully built, we would feed it with the real numbers and run it. So inside something called as the session. So advantage of this approach is that because the whole computation is known in advance, the framework can optimize it heavily before ever running it. Right. So, for example, combining the several small operations into one faster operation, a technique referred to as the operation fusion. Correct. So, this is what the technique is. Then we have in a tensor 2.x, the default behavior change into the eager execution. Right. The previously, which I have explained, it was the tensor 1.x operation. Now we will see the tensor 2.x operation. So in this tensor 2.x operation, the default behavior changed to the eager execution. That means, let me tell you what does this eager execution mean. So it means the operations, they run immediately line by line, just like the ordinary Python code. So we type A plus B and it computes the result on the spot. So no separate graph building stage required. So this makes the TensorFlow far easier to debug because we can inspect the intermediate values as we run the code, right? The same way we would with the normal Python program. However, in this case, the TensorFlow still allows us to get the performance benefits of the old static graph approach when we want them through a decorator called as the @tf dot function. So with this @tf dot function, we may go back to the version 1 where we build the graph and then execute. So when we place this decorative above a Python function, the TensorFlow uses a mechanism called autograph to trace our code and automatically convert it into an optimized graph behind the scenes, giving us the best of the both approaches. Right. So here we have the scalability. Correct. In this document, we can see over here, there is a scalability which is referred. So scalability is a strength, right? So it is referring to the TensorFlow's ability to spread a single training job across multiple CPUs. See, again, I will repeat, we are looking the basic component of our neural network, which is called as the tensor. Here we are learning different packages, but these packages, all these packages are built on the tensor. And we all talk about the word as a tensor, but we are not aware what was the tensor is all about. So just now I have explained you what was the tensor, what are the various versions, features of the various versions of the tensor. Now we are looking into the scalability strength of the TensorFlow. So scalability strength, it is referred to as the ability to spread a single training job across the multiple CPUs, GPUs, and which are doing many small arithmetic operations simultaneously, right? And again, these TPUs also, the tensor processing units, which are custom chips by the Google, specifically to accelerate the tensor operations even further than a general purpose GPUs. Correct. So scalability, what does the scalability means? The scalability means the TensorFlow's ability to spread the single training job across CPU, GPUs, and TPUs, whatever is available with us. Then there is a deployment ecosystem. This ecosystem refers to a family of the companion tool that let a training model be used in the real world setting beyond the training script. So TensorFlow serving is a system for hosting a training model on a server. So other application can send it data and get the predictions back. Even there is a TensorFlow Lite. This compresses and optimizes the model so it can run directly on a mobile phone or the embedded device with the limited computing power. Then there is a TensorFlow.js, which allows a model to run directly inside a web browser using JavaScript. Even we have the TFX, which is the short form of the TensorFlow extended, and is a toolkit for managing the entire life cycle of the machine learning project in the production. So from the data validation through the training through the deployment. So often it is referred to by the umbrella term MLOps. MLOps, that is my machine learning operations. So this practice is managing the ML, that is my machine learning system, reliably at this scale. Right. So then let's look at what is this tensor board. So this tensor board is a TensorFlow's built-in visualization tool while a model trains. So tensor board can display live graphs of the things like the loss value dropping over the time, histograms of how the weights are distributed, and even a visual diagram of the computational graph itself. Right. And then we have the tf.data API refers to a set of tools for building the efficient input pipelines. So the process of reading the raw data from the disk, shuffling it and batching it into the groups and feeding it into the model in a way that keeps the GPU constantly busy instead of waiting around for the data to be prepared. So this is all about the tensor. So let me explain again what we have learned in the tensor. So the tensor is a basic term which means our data. So it can be multi-dimensional tensors. As I said, the single dimension, that is single element is my scalar or zero-dimensional tensor. Then there is a list, which is my vector, which is one-dimensional tensor. And like this, I have the stack of the matrices also, which is my multi-dimensional tensor. In the tensor, during the initial days, as we said, the tensor flow of version one, the graph is the code is written, the graph is computed from the code, and then the tensor, that is my data, is fed to this graph to do the operations. Then in tensor 2.x, there is a eager execution where the it do the task like a Python line by line compilation is done. Over here again we have some decorators which are like at the rate tf dot function, so which can ask you to behave like the autographs also, which was my first version, that is 1.x version of TensorFlow. There is a scalability in the TensorFlow. So what does it mean is TensorFlow can work on GPUs, CPUs, and TPUs. It has that capacity to spread the task across the multiple processors. There is a TensorFlow ecosystem. So we have the serving ecosystem, we have the Lite.js ecosystem, we have the TFX, and then we have the MLOps ecosystem. Then there is a tensor board, which is for the visualization tool. And then we have the tf.data APIs, which is the set of tools for building the efficient input pipeline. So this is all about the tensor. And now we will go to our packages, our actual packages. So first package, as we have said, so this was all about the tensor, as we have explained just now. You must have seen this, that it is a Google Brain in 2015. It is a computational graph based, and then 2.x uses the eager execution. There is a scalability term. Then there is a deployment ecosystem, as I explained. Then we have the visualization and tf.data APIs, and then the language support, which are given for the TensorFlow. And so the typical use of the TensorFlow is the large scale production, mobile edge inferences, and the industry machine learning ops pipeline. Then we have the Keras. Now look at this. What does this Keras mean? So let me go back to the concept of the Keras. So Keras was created by Francis Collard after release in 2015, and is the best understood as the high level API sitting on the top of more complex underlying engine. The term API is a simple, which is my application programming interfaces. and it is a set of commands and functions a program is allowed to use to interact with the piece of the software without needing to understand the underneath hardware or underneath philosophy. So Kera's entire philosophy is to hide the complicated tensor and the graph mechanism of the TensorFlow behind the extremely simple and readable commands. Right? So that's how the Keras works. So let me explain you about the Keras 3. Let me scroll down this image. I hope you all are able to see. Okay, I think I need to share it again because you all are not able to see the diagram. Okay, just give me. Okay, now you are able to see this Keras, right? So we'll explain this Keras again. Means I'm explaining this Keras. So this Keras, which we are explaining over here, is the Keras 3, the current generation, and this is my multi backend. It means that exact the same Keras code we write can be executed using the TensorFlow. So PyTorch or a newer frameworks like the JAX as the actual computational engine underneath. So without us to need to know about like what is there behind this, how does the basic graph creation works or etc. So that is why the architecture diagram places a backend engine layer at the very bottom of the Keras task. So Keras itself does not know how to do the actual mathematics. It simply handles the work of to the whichever backend is currently selected. There is a modularity concept, which means the every piece of the Keras model, each layer, each loss function, each optimizer is built as an independent swappable object, so we can mix and match them the way we might want to mix and match, right? Then, then there are two main ways of assembling these bricks mentioned in the document as the sequential API, right? So where you simply stack layers one after the another in a straight line. And then we have the functional API, which allows more complex steps, such as a model with multiple outputs or the layers whose outputs get reused in more than one place. So something a simple straight stack cannot represent, correct? So these are the two ways to assemble these Keras. Then we have the callbacks. These callbacks are the small pieces of the code that Keras will automatically run at the specific points during the training. For example, at the end of every uh, epoch, right? Then we have also mentioned the early stopping. So what does it mean is it halts the training automatically if the model's performance on the validation states set stops improving, preventing the wasted time and the phenomenon which is called as the overfitting. Then where the model start memorizing the training data rather than learning the general patterns. So this is my concept for the early stopping, which is supported by the Keras. Then we have the model checkpoint. So it automatically saves the model's weight to the disk at the intervals. So we do not lose the progress. And if something crashes, right, this model checkpoint will be used to save the data till that point. So there will not be a problem after any of the crash. Then we have the reduce LR on plateau, which automatically shrinks the learning rate. What does it mean is the size of the steps taken during the training. So when progress stalls, which often allows the model to fine tune itself more precisely. So these are the different terms which are, these are the different parameters or features which are available with us to the Keras. So again, I will repeat, this Keras is developed by the Charlotte in 2015, and then the Keras 3 supports the TensorFlow, PyTorch, and JAX backend. It has the fast prototyping via sequential or functional API. Then there is modularity through the layers, optimizers, losses, matrices. Then backend flexibility is of course there. Then there are built-in data sets also which are available with Keras, that is MNIST, CIFAR, then IMDb via Keras dataset. And there is a callback functions, so early stopping, model checkpoint, and reduce LR on plateau. So these callback functions are specifically used to prevent the overfitting, to prevent the uh, shrinking the learning rate. So these are the different functionalities which are available for us through the Keras. So this is typically used in the teaching and rapid prototyping. Then we have the Theano. This Theano is developed at the University of Montreal starting in 2007 and it is historically important, but it is explicitly flagged in the document as a discontinued from 2017. So now the Theanos is not used, it is discontinued, meaning no further update, bug fixes, or the compatibility patches have been released for it. It is included in the study just for the study purpose and it is not at all used currently. So Thynos' core idea was the symbolic computation. In the symbolic computation, this it is its own core idea. And so in the symbolic computation, we write mathematical expressions using the placeholder variable that do not yet hold any actual numeric values. So describing a formula in abstract, similar to writing the algebra equation on paper before plugging in numbers. So we only when we use the compile this expression using the Thino dot function and supply the real numeric tensor, does any actual computation take place. So this is the strictest possible version of the defined and run philosophy, which we have discussed. Then the Thino is pioneering automatic differentiation, which means that it could look at a formula and automatically work out the mathematical derivatives of that formula with respect to any variable inside it, which is exactly what is needed to train a neural network through a process which is called as the backpropagation. Correct? The algorithm that calculates how much each individual weight in the network contributed to the final error, working backward from the output toward the input. That's my backpropagation. So the Thenos have the typical power of this automatic differentiation. So it can calculate this values automatically. So backpropagation is automatically calculated in the. Then we have the graph level optimization, which is refers to rewriting the Thynos without performing on the symbolic expression before compiling it. So such as the operation fusion and the numerical stability rewrite. So these are also the optimization features which are available with the Thynos. Then we have the PyTorch, the next package. Let me explain you about the PyTorch. I hope you do not have any doubt till here. So is there any doubt? Hello, students. Do you have any doubt till here? Or I can continue? Okay. So we'll continue. So there is a PyTorch. PyTorch was released by the Facebook's AI research division in 2016 and is now maintained under the Meta. It's defining characteristics repeated throughout the document and is the dynamic computational graph, which is also called as the define by run. So that's the most important characteristics of the PyTorch. Again, I will repeat this define by run, or it is also called as the dynamic computational graph, which is the most important characteristics of this PyTorch. So unlike the TensorFlow 1.x or Thyno, where the entire computation graph must be fully described before any real numbers are involved, the PyTorch builds its graph piece by piece in the real time as our ordinary Python code actually executes. So each time the tensor operation runs, the PyTorch silently record what happened as a new node in a temporary graph. So once we calculate a loss value and a call, which is called as a dot backward, the PyTorch walks this freshly built graph backward to compute the every gradient, and then graph is thrown away. So the next time when we run our code, a brand new graph gets built from the scratch. Right? I hope you have understood this. So what happens is over here, each time a tensor operation runs, a PyTorch silently record what happened as a new node in the temporary graph. So once we calculate a loss value and call this dot backward, the PyTorch walk this freshly built graph backward to compute my gradient, and then the graph is thrown away. So the next time we run our code, a brand new graph gets built from the scratch. So this is very practical benefit because the graph is just a byproduct of the ordinary Python execution. So we can use the normal Python tools like the debuggers, print statements, and conditional logics directly inside our model. So everything behaves exactly as it would in any other Python program. So this is why the document describes the PyTorch as feeling Pythonic and notes it has the native support for the variable length input, which matters enormously for things like processing sentences of a different length in the natural language task. Then it has the torch.tensor. This torch.tensor is the PyTorch core data structure. So it is deliberately designed to feel almost identical to the NumPy's array object, a library which is like every Python programmer already knows. So the PyTorch tensor can additionally live on the GPU and can automatically track the operations performed on it in the gradient computation. Then we have the torch.autograd, or short for automatic gradient computation. It is an engine which is responsible for building that temporary graph and running backward pass, which we have described just now. And when we set requires grad is equal to true on a tensor, it we are telling the PyTorch to start tracking every operation involving that the tensor, so its gradient can later be computed. Even the torch script, it addresses the limitation of the dynamic graph approach because the graph only exists transiently while the Python is running. So we cannot easily save a PyTorch model and run it in an environment without Python installed. So PyTorch script solves this by converting our dynamic PyTorch code into the fixed serializable representation that can be saved to the test. And it can be loaded later without needing the original Python source code. Right. So finally, the ecosystem terms the Torch Vision, Torch Audio, and Torch Text. These are the companion libraries. Just give me a time. Okay, so it is a Torch Vision or the Torch Audio and the Torch Text. This is my ecosystem, which the on which the PyTorch is built on, and it is a companion libraries providing the ready-made data sets, pre-trained models, and the data processing utilities specifically for images, audio, and text. So PyTorch Lightning is a higher level wrapper that removes the repetitive boilerplate code from the training loop. Then we have the torch.distributed. You can see it from the document. So this torch.distributed provides the tool for spreading a single training job across multiple GPUs or even the multiple physical machines. Right. So these are my basic packages which we are supposed to learn through this study assignment. We'll look at the comparative summary table. So the developer, then the release year, the graph type, then the ease of use, then debugging. So the most important is my graph type. The Tensorflow is a static or the eager. The Keras is depend on the backward. Theano is the static, and the PyTorch is the defined by the run. So these are the basic architectural diagram. And then whether they support the mobile or edge support or the GPU support, etc. Now look at the architecture of this each. So the first architecture is the architecture of the TensorFlow. Here you are able to see this TensorFlow architecture. So let me explain you this architecture in a very short. Right. So over here, what happens in this architecture? So each of this architecture diagram are the framework as the vertical stack of layers, where each layer relies on the layer beneath it, and it provides the services to the layer above it. That's a simple common understanding of this architecture, right? So at the bottom of the TensorFlow and PyTorch diagrams sits the hardware layer, the physical GPU, CPU, TPU chips actually performing the arithmetics. Then the CUDA is the NVIDIA's programming platform that allows the software to send the instructions directly to the NVIDIA GPU. Then we have even the CUDNN is a companion library of highly optimized ready-made implementations of the common neural network operations built on the top of the CUDA. Then just above this hardware, there is a core runtime written in the C++ in both TensorFlow and the PyTorch. The reason is this layer is written in C++ rather than the Python. Right. Then you can see here we have this hardware layer, core layer, then distributed execution engine, then there a graph layer, and the API layer and the toolkit ecosystem, which we have seen just now. That's my architecture of the TensorFlow. Then we have the architecture of the Keras diagram. It is also again the same. Every time at the end, the bottom layer is my TensorFlow or the backend engine layer. And then there is a Keras core layer. Then there is a model building APIs layers and then training models. So they're specific to the package. So here the graph layer presents in the TensorFlow represent the computation as the directed acyclic graph, which is also called as the DAG. Fine. So this matters because it guarantees the computation has a well-defined order. We can always calculate every earlier value before you need it to the later steps. So in the Keras diagram, we can see that the model building API layer offers the sequential, functional, and subclassing approach. The subclassing term, which means that writing your own Python class that inherits from the Keras base model class and manually defining exactly how data flows through it inside a model method called as the call. Then we have the diagram for the Theano and then the PyTorch architecture diagram also, which is having the optimizer layer with it. You can see over here. So this PyTorch diagram that is diagram torch.nn.module is the base building block for any neural network layer. Every custom layer or the full model we write inherits from this class, which automatically takes care of bookkeeping tasks like tracking which numbers are trainable parameters. And then the optimizer layer, that is torch.optim, contains the actual update rule, that is SDG, that is my stochastic gradient descent, which we have seen in the theory, the simplest and the oldest trading rule. Even the Adam, which is the modern, generally faster converging update rule that automatically adjusts the step size for each individual parameter based on the history of its recent gradient. So these are the two most commonly used examples in the PyTorch. Now, comparing this architecture, so the TensorFlow, the graph is constructed eagerly, statically, and stressed. Keras delegated to backend, Theano the static, and PyTorch the dynamic core language on which this particular packages are built. So here we can see that this it is built on the C++ 4 and Python, pure Python. Then the Python front end, C, CUDA, and then C++ and Python. Then do does have the auto differentiation mechanism. So it is a gradient tape delegated to backend, symbolic differentiation, and automated. So like this, the three architectures can be compared. Now we have already seen this the tensor and how does this tensor flows. Still, still we can see over here. So again, we'll come back and visit to this basic operation, like what the tensor flow between the operation node means. You can see over here, the title is also written like, what does it mean? When I say the tensor flows between the operation nodes, so what does this exactly mean? So here we can see that in the diagram that there is X, W, matamal, Z, B, add, A, ReLU, and Y. These mean to take the abstract phrases, right? The tensor flow between this operation node, completely concrete. So reading it to left to right, the X is your input data and W are both are tensors, right? So drawn as a circle. They both feed into a box labeled called matamal, which is my matrix multiplication, which is a single most common operation in all the deep learning. So it is how a layer combines a input vector with its weight to produce a new representation. So result of this multiplication is a new tensor, which is called as a Z. I hope you are understanding the terms. Okay, I think the screen is not getting changed. Let me again go back to the screen. Just give me a time. So we will go back to the screen again. So over here, okay. So now the screen, just a second, just a second. I think we'll again share the screen. Mhm. There is the same. Yeah, here is the same. So now you will be able to see like this operation. And let me explain you what does this operation say. So we have see the data which flows is my tensor and these operations which we perform is my node. So it is the activation function, correct? So the computation diagram comparing the static graph to a dynamic graph visually enforces the earlier explanation. So static side. So there are three stages: define, compile, run, and happen strictly in this sequence with the entire computation fully specified before and actual data flows. So from the diagram, you can see that like what does the tensor mean? So tensor is flowing the data and the nodes are the operations which we perform. So there is the output of each operation and that is again a tensor. Now moving to the simple codes. So here it is a static graph and dynamic graph which we can see. And now see the simple code snippet for the tensor and for the Keras and for the Thynos. And as I say, the Thynos has been outdated. It is deprecated and now it is not at all used, but it's just a study package for all of us. And then lastly, we will look into the PyTorch sample code. Let me take it very quickly. So see, these all four code examples, they deliberately compute the same tiny neural network calculation, which is my y is equal to ReLU wx plus b, wx in w into x plus b, followed by computing the gradient of the simple squared error, so loss function with respect to the weights. So in the over here in the code of the tensor, see, you can see all these codes very easily. So the loss function is a formula that measures how wrong the model's current prediction is. And in the code snippet, the loss is equal to mean, which is my y minus 1.0 square is a simple version of what is called as a mean square error, right? So this is my loss function. Then it measures the average square difference between what the model predicted and what it should have predicted. So training a network essentially means repeatedly nudging the weight. So this loss value gets smaller and smaller. Then there is a gradient. So computed in every one of the four snippets. So it is a mathematical derivatives of the loss with respect to the particular weight. So in simple terms, it tells us exactly which direction and by how much we should adjust the weight to reduce the error slightly. Then we have the TensorFlow. If you look at the TensorFlow code, there is a TF.gradient tag. It is a special context and it is recording the device which is temporarily switched on and it watches the every operation. In the Keras code, you can see over here, again the simple code itself. So in this Keras code, the model.compile is where we tell the Keras which optimizer to use. It is the add-on which loss function to use. Then there is a model.fit, which actually runs the training loop for the specified number of epochs. So three in the given case. And so one epoch means the model has been every single training example once. So using the mini matches of the 32 exa examples at a time. Here we are running the code. The dropout layer used in the model defines is a regularization technique during the training, and it randomly temporarily switches off 20% of the neurons in that layer on each pass. So which forces the network to not rely too heavily on any single neuron and generally helps prevent the overfitting. The Thynos code is also there, but Thynos code, it is just for the study purpose, it is not been used. And then we have the PyTorch code. So in the PyTorch code, after computing the line loss dot backward triggers the entire automatic differentiation process, which we have described earlier. And the resulting the gradient becomes available as the dot grad on each tensor. That is my w dot grad and comma b dot grad. The second of this snippet demonstrates the second half code snippet. It demonstrates the more realistic production style approach of defining the proper class. So simple net that inherits from nn.module and shows the standard PyTorch training pattern. So run the model forward to get an output. So compute the loss by comparing it to the target. which is called as the optimizer.0.grad. So which clears out any old gradient left over from the previous steps. So since the PyTorch accumulates the gradients by default rather than automatically resetting them, then we call the loss dot backward to compute the new gradients, and finally call the optimizer dot step. So which is the line where the optimizer actually uses those gradients to update the model's weight. So this is what about the all the codes, and let us see like the comparison of this all codes, and then we'll look at the Google Colab compatibility for this code. Fine. So Google Colab is a free cloud-hosted platform from the Google that let us anyone write and run the Python code, including the deep learning code, in a web browser without installing anything locally. So it provides the free access to GPUs, which is why it is so widely used for teaching and our courses, right? So the document notes that Collab's environment already comes with the Python 2.3.12, the TensorFlow, PyTorch pre-installed, and that's why the TensorFlow, Keras, and PyTorch snippets can simply run without any step in the Google Colab. As I already said that Theano is the flagged as likely to be failed because it has not been updated since 2017, and so it cannot be used, correct? So now at the concluding line, right? So this is where our the first study assignment is getting over. So at the concluding line, I would like to say that there is a recommendation essentially distills everything about into the practical guidance. And the TensorFlow strength is taking a finished model and reliably running it at the large scale in the real world across many types of the devices. Then we have the strength of the Keras in letting the student or engineer to go from an idea to working trainable models in the fewest possible lines of the code. I know though it is outdated, it doesn't play any role nowadays. It is just purely for the educational purpose. And the PyTorch strength is giving the researchers maximum flexibility and easy debugging when they are inventing or experimenting with the genuinely new kind of the network designs. Which is why has become the dominant choice currently in our research part or in the academics part. Right. So thank you all. Do you have any doubt after this?